Okay, so let's dive deep into something really critical for building reliable apps, and honestly, a topic you will hit in senior tech interviews. Database transactions. And specifically, ACD guarantees.
Yeah, definitely. We've basically taken a bunch of material, articles, notes, and boiled it down. The goal here is really to get you feeling solid on this stuff, ready for those interview questions.
Right, because actually building things, you run into all sorts of, well, chaos.
Exactly. That's the thing. Your database can crash mid-operation, right? Or the app itself, network drops.
Oh, yeah, been there.
Multiple people hitting the same data at once. It gets messy fast. You might get inconsistent reads, classic race conditions, all that fun stuff.
Fun, yeah. So transactions are kind of like the safety net for all that.
Pretty much, they're this abstraction layer. They handle a lot of that error complexity for you. So instead of your app constantly worrying about, okay, did step 1 finish, but step 2 fail?
Which is a total nightmare to code for.
Yeah. Right. Transactions give you these safety guarantees. They make a whole bunch of steps act like one single thing. It's either all of it works or, none of it does. All or nothing.
All or nothing. Okay, I like that. Makes handling errors way simpler.
Yeah. They promise that if you group operations, either all of them commit successfully or none of them do. Now, while the core idea of AC sounds pretty straightforward, atomicity, consistency, isolation, durability, the tricky part's really in the details.
How so?
Well, as we'll get into, that term acity, it gets thrown around a lot. Sometimes it feels more like marketing than a super strict universal definition. Understanding that nuance is really important.
Okay, so let's peel back the layers then, starting right at the beginning.
Okay.
What is a transaction, fundamentally, in a database context?
So think of it like grouping. You're taking several reads, maybe several writes, and telling the database, hey, treat these steps as one logical unit.
Got it. So it's not just do A, then do B, then do separately. It's do A, B, and C together.
Yeah.
As a package.
Exactly, a package deal. And the really crucial part is this package deal has to execute completely or not at all. If everything inside succeeds, you commit it. Changes are permanent.
And if something goes wrong, like anything,
then the whole thing gets aborted. Or rolled back, same idea. The database automatically undoes any changes that specific transaction made. It puts things back exactly how they were before that transaction even started.
Ah, okay. And that's the big win for error handling, right?
Yeah.
If my transaction blows up, I know the database is still clean, no weird half-done state. I can just try the whole thing again later safely.
Precisely. You don't need application code trying to figure out, okay, what partial mess did I leave behind? How do I fix it? The database guarantees a clean slate after an abort. That all or nothing idea, that's the foundation. It's your starting point for ACID.
Which brings us nicely to the acronym itself. ACID. Atomicity, consistency, isolation, durability. Sounds solid. Came from Herter and Reuter back in '83.
That's the one. And right away, here's where that nuance kicks in. Super important for interviews. One database's version of ACID is not the same as another's. Seriously. It's used so broadly now, sometimes it really is just a marketing term.
So what's the alternative if something isn't ACID?
You often hear the term BASE. It stands for basically available soft state eventual consistency, which basically means it doesn't give you those strong immediate guarantees that ACID aims for.
Okay, so interview red flag number 1. Assuming ACID compliant means the exact same thing everywhere. Like database X's ACID is identical to database Y's ACID.
Bingo! That's a trap. What interviewers want to see is that you get the goal of ACID, but you know the actual implementation, the specific guarantees you get under that label. They can vary a lot. You got to look under the hood.
All right, let's pop that hood then. Starting with A, atomicity.
Okay, so atomicity and ACD. It's specifically about what happens if there's a fault while a transaction is running. Say you've done a couple of writes, but then boom, the process crashes, network cable gets unplugged, disk runs out of space, maybe you hit a constraint violation like a unique key conflict.
Right, something stops it before it can finish and commit.
Exactly. If that transaction can't reach the finish line, atomicity guarantees the database will abort it and automatically undo everything that transaction had written up to that point.
Now, this is where I sometimes get confused. How is this different from, say, an atomic operation in multi-threading, like atomically incrementing a counter in code?
Great question. And yeah, that's a super common point of confusion, definitely an interview. Gotcha. Let's be crystal clear. ACID atomicity is not about concurrency. It's not about multiple threads hitting the same data at the same time.
Okay, so what is it about then?
It's purely about fault tolerance. It guarantees that if a failure happens mid-transaction, you're not left with a half-baked result. The database goes back to the consistent state it was in before the transaction even started. Some folks argue abortability would have been a better, less confusing name.
Abortability. Yeah, that actually makes a lot more sense. Okay, so it's about clean recovery from failures. Can we walk through that email mailbox example? That seemed helpful.
Sure thing. Imagine you're building an email app. New email comes in. You need to do two things in the database, right? One, insert the email itself into, say, an emails table. Two, you update the unread count in the recipient's mailboxes table. Two separate steps.
Okay, so I start a transaction, group them. Step 1, insert the email. Database says, yep, done.
Right. But now, step 2, you try to update the mailbox count, and just then, maybe the server runs out of disk space, or the application process crashes. Whatever it is, that second operation fails. The transaction can't commit.
So without Atomicity, I'd have the email in the database, but the unread count would still be the old value. The data is inconsistent from the app's point of view. There's an email there that the count doesn't reflect.
Exactly. That's the inconsistent state you want to avoid. But with Atomicity, when that second step fails and the transaction aborts, the database automatically rolls back the first step to the successful insert. Poof! It's like a whole transaction never even started.
Okay. The database is back to exactly where it was before I tried to add that email. No partial changes left behind.
Precisely. It's like that magic trick analogy, Either the whole illusion works perfectly, or if something goes wrong, everything instantly resets to the start. The audience never sees the half-finished setup.
That's a good way to think about it. Okay, so if an interviewer asks, explain Atomicity in ACID and give an example, that email scenario works well. And the red flag is, don't mix up ACID Atomicity with, thread safe counters.
You got it. Two different concepts.
Okay, on to C. Consistency. This one always feels a bit fuzzy.
It is. It's definitely the most subtle of the four. So in the ACID context, consistency basically means a transaction should take the database from one valid state to another valid state.
Okay, but what defines valid?
That's the key. Valid is defined by your application's rules. Your invariants. These are like statements about your data that must always be true. For instance, in a bank transfer, the money debited from one account must exactly equal the money credited to the other account within that transaction. That's an application invariant.
But wait, the database doesn't know my specific business logic, right?
It
can't enforce that my debits and credits balance if my application code messes it up inside the transaction.
Exactly. You've nailed it. And that's a crucial point often probed in interviews. Is ACID consistency a guarantee from the database or the application? Why? And the answer is, it's mostly an application property. Yeah. The developer writes the transaction logic to maintain those invariants. The database helps by providing atomicity, isolation, and durability, the A, I, and D. These help the application achieve consistency. But the database itself, it can't magically enforce all your application's specific rules.
So the database gives you the tools, no half-finished states, atomicity, no weird interference, isolation, doesn't lose your committed data, durability, and then I use those tools to build transactions that keep my application data consistent.
Precisely. The database can enforce some basic consistency things. Think foreign keys, unique constraints, not null rules, things defined in the schema. But those complex multi-step business rules, that's on the application logic. Honestly, some people think the C was maybe just stuck in there to make the acronym spell ACD.
Could be. It is catchy. Okay, so the red flag here. Thinking the database guarantees all consistency just because it says ACID, you need to understand it's a partnership between the database guarantees, AID, and your application logic, C.
Spot on. Database provides the foundation. Application builds the consistent house on top.
Right. Let's move to I then. Isolation. This feels like it's all about concurrency, right? Multiple things happening at once.
Exactly. Isolation tackles the headaches that come when multiple transactions are running concurrently. It basically means that transactions shouldn't mess with each other. They should be, isolated. This is where we get into things like race conditions.
Okay, define a race condition in this context. How does it happen in a database?
So a race condition happens when the result of something depends on the unpredictable timing of different processes or transactions. If they run in a slightly different order or overlap in just the wrong way, you get an incorrect result. That counter increment example is perfect here.
Walk me through it again. Two users hitting on something at the same time.
Yeah, something like that. They both want to increment a counter. So user A reads the counter value. Let's say it's 42. User B reads the counter value, also 42.
Okay, they both see 42.
Now, user A's application calculates 42 plus 1 equals 43. User B's application also calculates 42 plus 1 plus 1 equals 43. Then user A writes 43 back to the database. And right after, user B also writes 43 back to the database.
So the final value is 43. But it should be 44 because 2 increments happened, 1 got lost.
Exactly. That's a classic lost update race condition. It happened because the reads and writes weren't properly isolated. They both read the old value before either could write the new one back.
Nasty. Okay, another isolation problem mentioned was a dirty read. What's that about?
A dirty read is when transaction A reads data that was written by transaction B, but transaction B hasn't committed yet. It's reading uncommitted, potentially temporary data.
Why is that bad?
Because if transaction B later aborts the data that transaction A read, well, it never really existed in a permanent state. Transaction A based its actions on dirty data that was rolled back.
Let's use the email example again. User 1 is adding an email and updating the counter in a transaction, but hasn't committed. User 2 comes along.
Right. So user 1 starts their transaction, inserts the email. Now, before user 1 updates the counter or commits, user 2 starts their own operation, maybe just to display the inbox contents and the unread count.
Okay, so user 2 reads the emails table and sees the new email user 1 just inserted, even though it's not committed.
Potentially, yes, depending on the isolation level. That's the potential dirty read right there. Then user 2 reads the mailboxes table for the unread count. If user 1 hasn't updated the counter yet, user 2 sees the old count, maybe 0.
So user 2's view is messed up. They see the new email, but the count is wrong, still 0.
Yeah.
And if user 1 then aborts, user 2 read an email that technically never got saved.
Exactly. That's a clear violation of isolation. Transaction 2 saw the messy, intermediate, uncommitted state of transaction 1.
So what's the ideal solution? How should isolation work?
The theoretical gold standard is called serializability. It's a guarantee from the database that the end result of running a bunch of transactions concurrently is identical to the result you'd get if you ran them one after another, serially, in some order. It's like each transaction gets the whole database to itself while it runs.
That sounds amazing. Why don't we just use that all the time?
Performance. Serializability often comes with a pretty significant performance cost. To guarantee that, as if serial behavior, the database usually has to do a lot more locking, which can really slow things down when many users are active. So it's rarely the default.
The trade-off strikes again. So
Yeah.
what do most databases use? Weaker isolation levels.
Exactly. They offer weaker isolation levels that provide some protection, but allow certain types of race conditions or anomalies in exchange for better performance.
Like what kind of levels?
Common ones you'll hear about are read committed, which prevents dirty reads, but still allows other issues like lost updates or seeing different data if you read the same row twice in one transaction. And then there's snapshot isolation, often better. It gives each transaction a consistent snapshot of the database as it was when the transaction started. It prevents dirty reads, non-repeatable reads, and often lost updates, but it's still not technically serializable and has its own edge cases.
So stronger isolation, safer, but maybe slower. Weaker isolation, faster. But you, the application developer, need to be aware of potential weirdness.
That's the fundamental trade-off. It's a core system design decision. Think of that cooking analogy again. Serializability. Each chef gets the entire kitchen one at a time. Snapshot isolation. Everyone cooks at once, but when you look at someone else's station, you only see the ingredients they started with, not their current mess. Read committed. Maybe you can see their station, but you can't taste anything until they plate it. Dirty reads would be like tasting their half-mixed batter before they're done.
Okay, that helps visualize it. So interview questions likely revolve around: describe a race condition like a lost update and how isolation helps. Or, what's a dirty read? Why is it bad? And definitely, is serializability the only option? What are the trade-offs with weaker levels? Big red flag. Thinking serializable is always on, or the only way.
Absolutely. Show you understand the spectrum and the performance implications.
Core. Last letter, DF for durability. This one seems simplest: save the data.
That's the core idea, yeah. Once a transaction successfully commits, its changes should stick around. They shouldn't be lost, even if the power goes out or the database crashes right after confirming the commit.
How do databases actually achieve that? Just writing to disk?
Writing to non-volatile storage, yeah, a disk or SSD is key. But it's usually more than just that. Most databases use something called a write-ahead log or WAL.
Write-ahead log.
Yep. Before the database modifies the actual data files on disk, it first writes a description of the change to this log file. The log write is usually faster, more sequential. So if the database crashes after writing to the wall, but before updating the main data files, when it restarts, it can read the wall and replay any committed transactions that didn't make it to the main files, ensuring their changes are applied. Or it can use the log to undo changes from transactions that were in progress but didn't commit.
Okay, so the wall is crucial for recovery. What about systems with replicas? Multiple copies of the data.
Good point. In replicated setups, durability often means the data isn't just written locally, but it's also successfully copied to one or more replicas on different machines. The database might wait for confirmation from a certain number of replicas before it tells the client, yep, your transaction is committed and durable.
But even with walls and replication, is perfect durability actually possible? The sources seem skeptical.
Right, and that's an important nuance. Perfect, 100% guaranteed durability probably doesn't exist in the real world. Durability is about making data loss extremely unlikely, not impossible.
What could still go wrong?
Think about correlated failures. A massive power outage hits your whole data center, taking out the primary and all its replicas at once. Or weird hardware bugs. Some SSDs had issues with data loss on power failure under certain conditions, firmware bugs. Or even just slow, subtle data corruption, bit rot. Over time, that might affect backups too if not carefully managed. And, human error deleting the wrong thing is always a possibility.
So it's defense in depth again. White wall, plus disk writes, plus replication, plus backups, hoping at least one layer saves you.
Exactly. It's a layered approach to risk reduction. So, for an interview, how is durability typically achieved? Talk about non-volatile storage, walls, replication. What are the limits to perfect durability? Mention correlated failures, hardware issues, the need for robust backup strategies, the red flag, claiming absolute guaranteed data safety just because a transaction committed.
Got it. Show you understand the practical limits. Okay, we've talked a lot about transactions changing data. Does it matter if I'm changing just one thing versus like 5 things at once?
Yeah, that's a really important distinction. Single object versus multi-object operations. Atomicity and isolation get much more complex and frankly more necessary when your transaction needs to touch several different pieces of data, like multiple rows, multiple documents, multiple keys.
Why would I need to change multiple things in one transaction anyway?
Because keeping your application data consistent often requires keeping different bits of data synchronized. Think about that bank transfer. You need to decrease one balance and increase another. That's 2 objects. Or our email example. Insert the email and update the unread counter. 2 objects.
What about database internals, like indexes?
Perfect example. When you update a record, the database also has to update any secondary indexes that point to it. Those index entries are separate objects, so even a simple-looking update might require multi-object atomicity and isolation behind the scenes just to keep the indexes consistent with the data.
Okay, that makes sense for multiple objects. But what if I'm just updating, say, one big JSON document, like 20 KB of data? Do I still need transaction stuff?
You still need some guarantees, yes. Even for a single object, you need atomicity to ensure the write either completes fully or not at all. You don't want a crash leaving you with a half-written, corrupted JSON document. That's single object atomicity.
And isolation.
And you need isolation so that if someone else reads that JSON document while you're in the middle of writing your 20 KB update, they don't see some weird, inconsistent intermediate state. That's single object isolation.
How are those single object guarantees usually done?
For atomicity against crashes, databases use internal logging, maybe similar to a wall, but focused just on that object's changes. For isolation during concurrent access, they'll typically use locks on that specific object while it's being modified.
The sources also mention things like increment or compare and set. Are those transactions?
Ah, good catch. So operations like atomic increment or compare and set, you see this a lot in key value stores, provide atomic guarantees for one specific operation on one specific piece of data. Compare and set is like saying, update this value to Y, but only if its current value is X. It helps prevent lost updates on that single value without needing a full transaction.
But they're not full multi-object transactions.
Exactly. And that's another potential interview anti-pattern, confusing these single-object atomic ops with full transactions. They're sometimes marketed as lightweight transactions or even ACID, but they only work on one object at a time.
Right. So increment is fine for a simple web page counter.
Mm-hmm.
But for transferring game items between 2 players' inventories, that needs a proper multi-object transaction because you're coordinating changes across 2 inventories, 2 different data objects.
Precisely. The need for multi-object transactions pops up whenever your application's correctness depends on synchronizing changes across multiple distinct pieces of data.
Okay, so I've decided I need a multi-object transaction. How do I actually group the operations? How does the database know what's part of the transaction?
The traditional way, and still very common, is tying it to the client's database connection. You issue a begin transaction command, then all your SQL statements on that connection are part of the transaction until you issue either commit or rollback.
What's the downside of tying it to the connection like that?
Well, network glitches are the classic problem. Imagine you send the commit command, the database receives it, does the commit successfully, but then the network connection drops before the database can send the OK message back to you.
Oh, no. So my application is just hanging, doesn't know if the commit worked or not.
Exactly. Did it commit? Did the connection drop cause an implicit rollback? You're left in an uncertain state. It's a pain.
This is a better way.
Yeah, more modern systems, especially distributed ones, often use explicit transaction identifiers. The transaction isn't tied just to the connection, so maybe you could reconnect and check the status of the transaction using its ID. Much cleaner.
Okay, speaking of things going wrong, error handling and retries. This feels super critical for robust apps.
Absolutely. And the beauty of Atomicity is that if a transaction aborts, you know nothing happened. The database is clean. So the simplest, safest strategy is often just retry the whole transaction again.
Sounds easy enough, but I bet there are catches. What are the things you really need to consider when implementing retry logic? Feels like prime interview territory.
Oh, it absolutely is. And just saying, oh, I'll just retry is a bit of a red flag. You need to show you've thought deeper. There are several key things.
Like what?
Okay, first, what if the transaction actually succeeded, but you just didn't get the confirmation message back, like in that network drop scenario? If you blindly retry, you might do the whole thing twice.
Right, like charging a credit card twice. Bad.
Very bad. So your application might need ways to detect or handle duplicate submissions. Maybe make the transaction idempotent if possible, meaning running it multiple times has the same effect as running it once. Or use unique IDs to detect duplicates at the application level.
Okay, idempotency or deduplication, what else?
Second, what if the error was because the database was overloaded? If you just immediately retry, you're adding more load, making the problem worse.
Yeah, that's unhelpful.
So you need things like retry limits, don't retry forever, exponential backoff, wait longer between each retry attempt, and maybe special handling for database too busy errors, perhaps shedding load or failing faster.
Makes sense. Back off and give it space. Anything else?
Third, and this is crucial, you need to know why it failed. You should generally only retry transient errors, temporary glitches. Things like a deadlock, where two transactions are waiting for each other, maybe a temporary network hiccup, an isolation violation, like a serialization conflict, or maybe the database node just failed over to a replica. These might work if you try again.
But some errors won't just fix themselves.
Right. You should not retry permanent errors, like trying to insert data that violates a constraint. For example, duplicate primary key. Or maybe a data type mismatch. Retrying those will just fail again instantly, wasting resources. Your retry logic must be able to tell the difference between transient and permanent errors.
Okay. Differentiate error types. One more.
Yeah. Fourth, what about side effects outside the database? If your transaction logic also sends an email or calls some external payment gateway API, those things might happen before the database transaction commits.
Uh-oh. So if the database transaction then aborts, the email might have already gone out.
Exactly. The external action happened, but the database state rolled back. Simple retries don't fix that coordination problem. You might need more advanced patterns here, like two-phase commit, 2PC if the external system supports it, or maybe using transactional outbox patterns with message queues.
Wow, okay. Retries aren't so simple after all. So a key interview question is definitely, what are the potential issues and necessary considerations when implementing retry logic for database transactions? And the anti-pattern is naive, just retry everything. You need to talk about idempotency, backoff, error types, and external side effects.
Precisely. Sure you grasp those complexities.
Let's zoom out a bit. We've mostly talked about single databases. How does all this ACD stuff, especially multi-object transactions, work in big distributed systems? Systems spread across many machines.
Yeah, that's where things get significantly harder. Implementing atomic, isolated transactions across multiple nodes or partitions in a distributed database is a major challenge. Historically, this difficulty was a big reason why many early NoSQL databases just didn't support
They
them.
traded consistency for other things.
Exactly. They often prioritized availability and partition tolerance, the A and P, from the CAP theorem, over immediate consistency. They figured dropping multi-node transactions made it easier to scale and stay available, even if parts of the network failed.
So that's where the whole NoSQL means no transactions idea came from, or transactionless scalability.
Kind of, yeah. Though that phrase can be a bit misleading. It's not really true that transactions fundamentally prevent scaling, or that they're impossible in distributed systems. It's just that distributed transactions are complex. They often add latency or have potential availability drawbacks compared to single-node ones. But they can be done.
How? Are there specific techniques?
Yeah, the classic algorithm is two-phase commit, or 2PC. It's a protocol designed to coordinate an atomic commit across multiple independent systems or nodes. It involves a coordinator asking all participants if they can commit, and only if everyone says yes does it tell them all to actually commit.
Sounds complicated. And probably has its own failure modes.
It does. For instance, if the coordinator crashes at the wrong time, the participants might be left blocked, unsure whether to commit or abort. But it's a well-known mechanism, and there are other approaches too. The point is, distributed transactions exist, but they come with costs.
So that core trade-off we keep mentioning, strong consistency versus performance and availability, it just gets amplified in distributed systems.
Massively amplified. Choosing your consistency model and transaction strategy in a distributed system is one of the biggest architectural decisions you'll make. Do you really need immediate, perfect consistency across all nodes? Or can you live with weaker guarantees, maybe eventual consistency for some things, to get better performance or uptime?
It really depends on the specific needs of that feature or data.
Exactly. There's no single right answer.
Okay, this is great context. Let's try to solidify it with a couple of interview simulations, like we planned.
Sounds good. Let's do it. Okay, first scenario for you. Imagine you're designing a system for managing online game inventories. When a player trades an item with another, you need to remove it from player A's inventory and add it to player B's. How would you design this operation to ensure no items are duplicated or lost, even if the database or application crashes during the trade?
Okay, game inventory trade. Remove from A, add to B. Right away, I see I'm changing data in two distinct places. Player A's inventory record and player B's inventory record.
Good. Two distinct objects being modified.
And the core requirement is the item can't end up in both inventories, duplicated, and it can't disappear entirely, lost. It has to move cleanly from A to B or not move at all. This screams indivisible operation.
And what database feature gives you that indivisible all-or-nothing behavior?
That's got to be a multi-object transaction. So design would be start a transaction inside the transaction. First, update player A's inventory to remove the item. Second, update player B's inventory to add the item. Finally, commit the transaction.
Okay. Now, what happens if the server crashes after you've removed the item from A, but before you've added it to B? The transaction hasn't committed yet.
Right. Because of atomicity, the A in ACD, the database knows the transaction didn't complete successfully. So when the system recovers, it will automatically roll back all changes made by that incomplete transaction. That includes rolling back the removal of the item from player A. The net effect is zero change. The item is still safely back in player A's inventory, exactly where it started. Nothing lost, nothing duplicated.
Excellent. Now, think about concurrency. What if player A is trying to trade item X to player B, and at the exact same time, player C is trying to trade that same item X, which maybe they don't realize A is trading, to player D?
Ooh, yeah, race condition. Two transactions trying to modify the state of the same item concurrently. This is where isolation of the I becomes critical. Without proper isolation, both transactions might read the item's initial state in A's inventory. Both might proceed, assuming they have the right to move it, and you could end up with, well, a mess. Maybe the item ends up duplicated, or maybe one transaction overwrites the other's result incorrectly.
So how does isolation help?
The database's isolation level needs to prevent this interference. Ideally, for something like inventory management, where correctness is paramount, you'd want a strong isolation level, maybe even serializability for operations involving specific items or inventories. This would ensure the trades happen effectively one after another, preventing the race condition. If full serializability is too slow, you'd have to carefully analyze the guarantees of a weaker level, like snapshot isolation, and see if it prevents this specific race condition, or if you need to add application-level locking or checks. But the core database mechanism is using a transaction with an appropriate isolation level.
Perfect. You identified the need for the multi-object transaction, explained atomicity for crash recovery, and crucially linked isolation to preventing the race condition, even mentioning the trade-offs of different isolation levels. That's a solid answer.
Okay, cool. Let's try the conceptual one. Some distributed systems claim eventual consistency. How does that differ fundamentally from the consistency and isolation guarantees aimed for in ACID? And in what scenarios might eventual consistency be acceptable?
Great question. It gets right at the heart of different data philosophies. So let's break it down. ACID consistency, as we discussed, is mostly about the application ensuring its invariants hold true at the boundary of a transaction commit. And ACID isolation is about preventing concurrent transactions from interfering with each other and seeing weird intermediate states. The focus is on strong guarantees, usually immediate, within the scope of a transaction.
Right. Things should be correct and isolated right after the commit.
Exactly. Now, eventual consistency, which you often see in base systems, completely relaxes that immediacy. When you write data, the system makes it available, eventually. There's no guarantee that if you read from a different replica right after a write, you'll see that write, or that two different readers will see the same thing at the same time.
So it might take time for changes to spread, and you might read old data for a while.
Precisely. The only promise is that if writes stop for a while, eventually all the replicas will converge to the same state. But there's no hard guarantee on how long eventually might take. It trades off that immediate consistency and isolation.
What does it trade them for? Why would you want that?
Usually you're trading them for higher availability and better performance, especially in systems spread across wide geographical areas. Enforcing strong, immediate consistency across many distant nodes is really hard. It often requires complex protocols like 2PC, or it might mean you have to reject writes or make reads wait if some nodes are temporarily unreachable. That hurts availability.
So eventual consistency lets the system keep accepting writes and serving reads, even if there are network partitions or node delays, and it just sorts out the consistency later.
Pretty much, yeah. It prioritizes being available over being immediately consistent everywhere.
Okay, so when is that trade-off actually okay? When is eventual consistency acceptable?
It's acceptable when the application can tolerate temporary inconsistencies or reading slightly stale data. Think about things where immediate perfect consistency isn't absolutely critical, like the number of likes on a social media post, or maybe seeing a new comment appear slightly later on one device than another, your own profile updates propagating, maybe product recommendations on an e-commerce site.
Stuff where it's not the end of the world if things are a little out of sync for a short time.
Exactly. But for things like financial transactions, your bank balance, or critical inventory counts where being wrong even temporarily could cause real problems like overdrafts or selling stock you don't have, that's where you typically need the stronger guarantees closer to A side.
That makes the difference really clear. It's all about the use case and how sensitive the data is to temporary inconsistency.
You got it. And being able to articulate that spectrum from strong ACD guarantees to relaxed eventual consistency and explain why you'd choose one over the other for a given problem, that's key for system design interviews.
Okay, fantastic. So we've really unpacked atomicity, consistency, isolation, durability. We've looked at single versus multi-object operations, how transactions are implemented, the complexities of error handling and retries, and how this all gets even trickier in distributed systems.
Yeah, and just to wrap up the core ideas, transactions are fundamental. They simplify building reliable applications by making groups of operations atomic and isolated. This helps you, the developer, maintain consistency according to your application's rules, and durability ensures committed data isn't lost.
And the absolute key takeaway, the thing I really need to hammer home for interviews, ACD sounds great, but its actual implementation is not standard. It varies hugely between databases. Don't just trust the label. You have to understand the specific isolation level being used, how durability is really achieved, how failures are handled.
Exactly. Mastering these concepts isn't just about knowing the definitions, it's about understanding the problems they solve, preventing race conditions, dirty reads, partial failures, and understanding the trade-offs involved performance versus safety and isolation levels, complexity in distributed systems, the nuances of retry logic.
Yeah.
Knowing that stuff is what gives you confidence in designing systems and talking about them in interviews.
It's showing you understand the why and the how, not just the what.
Precisely. And maybe here's a final thought to chew on, kind of building on what we discussed. We know the C and ASI consistency really relies on your application code being correct. And we know most systems use weaker isolation than perfect serializability because of performance. So how much of the actual safety and consistency we depend on in the real world really comes directly from the database's strict ACD promises versus how much comes from us writing careful defensive application code that works correctly despite maybe only having weaker guarantees from the database below.
Hmm, that's a really interesting question to ponder. Where does the responsibility truly lie? Okay, well, hopefully you listening found this deep dive helpful for your own interview prep. If you did, maybe give us a like. And definitely subscribe so you don't miss future deep dives into other key system design topics.
Yeah, and please drop a comment below if you have questions or if there are other topics you'd like us to tackle next time. Good luck with those interviews.